Okay, entropy. This is really the missing link in our theory. It is the basis for all change, really, physical and chemical. So the idea is that we start to look for numbers that are going to explain how disordered a system is and why a system will change. So, how the disorder of a system changes in a physical or chemical process. Okay? It's a lovely concept, entropy. So, the natural tendency of the universe is to become more disordered. Okay? If you think about it, you look at this scene, we all know, we've all experienced this, that if you don't constantly put some effort into something, it becomes disordered, disorganized. Okay? Now, in terms of chemistry, we talk about how many arrangements there are of the particles present. So, if we're talking about molecules, then the more randomly arranged they can be, the more entropy there is, the greater the entropy. And also, we can talk about how the energy within the material, the molecules, the atoms, how the energy is arranged, how it's distributed, and how random it can be distributed. Okay? So the idea is if a process is going to happen spontaneously, then the degree of disorder, the amount of disorder must increase. Entropy increases. So the universe tends to increase entropy, to increase disorder. Okay? We also need to think about what spontaneous means, but we'll talk about that soon. This is a second law of thermodynamics. The universe tends to disorder. For a process to happen, entropy has to increase. Okay? For the process to happen spontaneously. I've suffered this myself. Having small children, it's much better to have a low entropy toy than a high entropy toy. It takes energy to make this into something that's ordered and structured, whereas one thing obviously has got low entropy. So, in a closed system, the natural spontaneous change involves an increase in total entropy. What do we mean by spontaneous? Spontaneous process takes place without any continuous intervention from outside the system. Okay, that's important. The idea that it isn't affected continuously from outside. You may need some intervention to start a process going, but once it's going, no more intervention is required. It continues spontaneously. Okay, so it might need a kickstart to get it going. Let's talk about distribution of particles, distribution and disorder. So a good example is sheep in a field. And if you leave them, then obviously the amount of disorder will maximize. The white and the black sheep will completely mix within the field. So the natural tendency is for that to happen. Okay, that makes complete sense. Now, if we get a sheepdog involved, then the sheepdog is trained to separate sheep into groups. So imagine we could have a sheepdog that could separate the whites and the blacks. Okay, the sheepdog would have to put in some energy to separate them, but also, as their natural tendency is to mix and to randomly distribute themselves around the field, the sheepdog will continuously have to put energy in to keep them separate. Okay? Now, if we have to put energy into the system to create more order, then the reverse must be true. As the system becomes more disordered, energy can be released. Okay, it's two sides of the same coin. So putting energy into the system can increase order, it can decrease disorder. But if a system becomes less ordered, then energy can be somehow released. So we've talked about the distribution of particles, the random distribution, and the number of arrangements. Let's talk about energy. Energy comes in packets, quanta, and if you've got more packets, more quanta, then the number of possible distributions of the quanta must increase. So for a given sample of a substance, if you increase its energy, keeping everything else constant, if you increase its energy, then entropy, the total entropy, increases because you've got more energy quanta, and the more energy quanta you have, the more possible arrangements of that energy quanta. And there's quite a good link for you to have a look at. So if we take something like bromine, or any gas, in this case it could be nitrogen dioxide, it doesn't really look too much like bromine, does it? But it might be. Let's call it bromine anyway. We've got bromine gas in two gas jars with a tap in the middle. If I open that, then they will mix. Okay, let's talk about diffusion. If we have, for example, bromine gas in one jar, as shown, and a tap closed in the middle, then you know what's going to happen. If we open that tap, then spontaneously these jars are going to fill with gas, and we're going to go from this arrangement to this arrangement. Okay? Why? Well, because we've got many, many more arrangements of the gas in this case, so entropy, the entropy of the system has increased. Okay? The system adjusts to maximize entropy. So diffusion in a room between jars in the atmosphere, it will always shift in order to maximize the total entropy. Okay? It's not just dependent on the disorder of the system, we'll talk about that later. It maximizes the total entropy, the total entropy. Let's have a look at the entropy of some substances. The standard molar entropies for some common substances are 25 degrees C. And let's have a look at the numbers overall. Look, these are the gases, and the gases, you'll notice, compared to the other figures, the gases have got a high entropy. Okay, so gases within a system, gases are free to move. They move randomly, they expand to fill the space available, and they have many more possible distributions in the system. Whereas liquids are more ordered. Even though the particles can move around, they're more ordered. So within the liquid, the particles can move, there can be many arrangements, but there's less disorder than with gases. And with solids typically have a regular arrangement, a lattice, for example, and within that lattice there's a lot of order, therefore low entropy. A perfect example, look at diamond. You know the structure of diamond, it's tetrahedral arrangement, very ordered, very low entropy. Okay, you can plot how the entropy changes as we increase temperature. Okay, so if we look at this graph, and we'll talk about it in detail a little bit later, but you've got the lower entropy when it's a solid, a jump when it becomes a liquid, higher entropy, and then a bigger jump when it becomes a gas. So we can talk about, in this case, we can talk about both the number of possible arrangements of the particles present and the number of energy quanta we'll look at that in detail a bit later. Zero entropy, the third law of thermodynamics. The entropy of a perfect crystal, absolute zero, is zero. The scale has to start somewhere, doesn't it? So we had the second law of thermodynamics, that within a system, the spontaneous change was for an increase in the total entropy. We've got the third law. What was the first law? Well, you've had this for years, haven't you? The first law of thermodynamics. Energy is not created nor destroyed. It simply changes from one form to another, or it's transferred from one place to another. So that's been around for a while. You might have called it the law of conservation of energy. Okay. There's a zeroth law of thermodynamics. They put all of these laws together. So they had the first law, which is about energy, the second law, which was about an increase in disorder, so entropy. The third law, they felt that it was important to have this perfect crystal to start the entropy scale. But then they realized there was something fundamental that was allowing all of these laws to exist. Have a look at that website when you get a chance. The zeroth law. And the zeroth law essentially is about temperature. And it really, deep down, it's about the fact that temperature can be measured. Temperature can be measured as a scale. Now, obviously, we have different scales of temperature, but it exists as a quantity that we can measure. Okay? There are lots of ways to look at this. When we're measuring the temperature of something, we're not measuring its energy, its total energy. We're measuring the average kinetic energy of the particles at that particular place in the universe. So it's a quantity that we can measure. Okay? This is why it's the zeroth law, because temperature is fundamental. It's a measurable property of matter. We can measure temperature, essentially. Okay? Now we can look at these diagrams, and this is quite intuitive, but we can think about what's happening here. And if we've got two systems, A and B, at the same temperature, then there's no net flow of energy between them. So if we've got two systems, A and B, at the same temperature, no energy flows between them, no net energy. Energy will flow between them, but there's no overall energy transfer. Now, if B and C are at the same temperature, then again, there's no overall net flow of energy between them. And that means that between A and C, there also would be no overall net flow. Okay, and this is just different ways of showing that. A is in equilibrium with B, thermal equilibrium, B with C, so A with C. Here we've got a thermometer measuring two objects. If these two objects are at the same temperature, then the thermometer will measure the same temperature. There's no net flow of energy, they're all at the same temperature. Okay. Systems that are in thermodynamic equilibrium are at the same temperature. That's the zeroth law. It's a good idea with entropy to remember some specific examples of entropy, just to kind of give you a little bit of a reference. If you're given a question, you've got somewhere to start. So gases have high entropies. Why? Because they've got many more arrangements of the particles present. Reactions that produce gases will lead to an increase in the total entropy. Okay? Ionic substances, they increase their entropy significantly when they dissolve. Why? Because, again, many more arrangements of the particles present. When they're in a lattice, their entropy is low because they're highly ordered. When they dissolve, they become more disordered, so entropy increases. If we break down large molecules, we increase entropy. Why? Well, because we've suddenly got many more pieces from the original molecule, so many more possible arrangements of the particles present. the change in entropy of a system. So when you're looking at a process, ask yourself the question, does the number of possible arrangements of the particles present increase? And if it does, then the entropy of the system has increased. Ask yourself the question, does the number of arrangements of the energy quanta increase? But if we increase the number of energy quanta, we're going to increase the entropy. We've mentioned this before. A reaction in chemistry is considered to be spontaneous if it continues to happen without any continuous external influence. I'm not going to worry about the rate too much, but the idea is that once the reaction's going, if there's no external influence, the reaction keeps going, and we consider it to be spontaneous. Okay? These questions are thermodynamic questions. Kinetic factors obviously are to do with activation energy and rate. But now we've got to include entropy in questions of why processes happen. What's the driving force behind the process? Okay, so we can use ideas of entropy to explain what happens when sodium chloride dissolves. We have high order, so low entropy in the crystal. The ions dissolve in the water, so obviously they become much more disordered. However, the water molecules will arrange so that their dipole is in the right orientation to stabilize the ions. So that actually increases the order of these water molecules, which is something that we need to take into account in some cases. Okay, so there's definitely an increase in disorder of the ions, but then the water molecules hydrate them. That can have an effect. The water molecules hydrating the ions also, remember, it's exothermic. It causes them to be more stable, so energy can be released. Okay, ions in the lattice are ordered. Their arrangements, number of arrangements increases, entropy of the system increases. Okay, and there's a mention there of the water molecules. The person who wrote this obviously found the spelling of chemistry a bit tricky. But this is a very good example of an entropy-driven reaction. An airbag has to produce lots of gas very quickly. So when there's a collision, the gas is produced and it cushions the blow of the head against the steering wheel, for example. So if you look at reaction one has a massive increase in entropy because we've got lots and lots of gas produced. We've gone from a solid, this is a solid at room temperature, sodium azide it's called, and it produces 3 moles of nitrogen gas. And this is actually a liquid or vapor sodium. So there's a massive increase in entropy. Okay. That first reaction is entropy driven and it happens very fast. Then there's some potassium nitrate involved in this process, in this mixture. Why? Because it soaks up the sodium to produce these basic oxides, and then the basic oxides react with silica to produce this silicate, and it makes the mixture safer. Okay, and let's go back to this graph and we'll try and flesh out the details of the trends and the changes within. So we've got entropy up the y-axis. We'll call this our total entropy. Okay, let's go back to this graph and try and flesh out some of the details of the trends and changes. So we have entropy of the system up the y-axis, and we've got temperature on the x-axis. And Tm and Tb will be the temperature of melting and the temperature of boiling. Okay, so let's have a look at each of the sections. Here we have a solid. We're increasing the temperature, therefore there are more energy quanta, and the more energy quanta we have, the more possible distributions of the energy quanta, therefore entropy increases. So here, essentially, greater energy quanta, greater distributions, arrangements, and greater entropy. Then, there's a certain step, the first step, from solid to liquid. Obviously at this point at the melting temperature, then the particles which were in a regular, organized, ordered arrangement suddenly are free to move around. So they're not as ordered as they were. Therefore, disorder has increased rapidly. So there's a sudden jump in the entropy. The solid melts. Liquid particles can be arranged in many more ways, so entropy increases. As the liquid is heated, again, this is now an explanation in terms of energy quanta. So greater energy quanta, greater number of arrangements of the energy quanta, and greater entropy. Boom, the big step. There's another big step here. So the liquid, which is, has particles quite close together, it's relatively disordered, but they're still very close together. There's a sudden jump where the particles now are completely independent of each other and free to move. So there are many, many more distributions of the particles present. So there's a greater entropy. And then the final thing, obviously, as we increase the temperature of the gas, again, it's in terms of energy quanta, greater number of arrangements, distributions, therefore greater entropy. And that is all fairly coherent. It's a good thing to remember because it clearly indicates which of the two factors, the arrangement, the physical arrangement of the particles or the arrangement of the energy quanta, is actually the overriding factor for the change that's displayed. Right. Read the pages indicated and let all of these new concepts sink in and have a go at the questions.